Chapter 16, slides 8 through 20. In this section, we're going to look at more effects of conjugation on reactions we've already looked at in previous chapters. I'm going to go back to SN1. After looking at the NBS reaction and considering that you end up making a radical intermediate, you had to consider, before finishing the reaction, you had to consider the fact that this radical intermediate is conjugated and thus resonance ensues, giving different options for ultimately different products. Well, the same could be said for carbocations and anions as well. So we have to be careful when you have an intermediate that's charged and is in an allylic position, is conjugated. If we were to start with SN1, so here's our leaving group, right? If you had a leaving group and you form a carbocation, we can see that you get resonance between the carbocation, and this will lead to ultimately different products. Okay, this can be controlled, given the conditions, to favor kinetic or thermodynamic products. Now, I'm going to put this on hold for a second and just remind you that we have, this slide is here so that you're reminded that when you do an SN1 reaction, you form a carbocation, and if we're working with a carbocation that's conjugated, we have to consider resonance, just like we had to consider carbocation rearrangements. You have to consider all resonance forms before adding the nucleophile. In SN2, even though there's no intermediate, I'd like to point out that there is an effect on the efficiency or the rate of the reaction. What happens is that when the leaving group is on an allylic position, which it is here, the transition state is stabilized and assisted through this pi system next door, thus affecting the overall rate. So it's not that you're actually forming a carbocation, it's that the transition state is stabilized. So the energy required to get to the product, the transition state, is stabilized, lowered, for when the leaving group is at an allylic position. So you can see a 73-to-1 rate difference when your leaving group is at a conjugated allylic position. And this is due to the overlap of the double bond orbitals with the p orbital in the transition state. So that transition state is stabilized, thereby making it lower in energy. If we considered the acid-base reactions, where the base deprotonates the allylic proton, that is far more reasonable than trying to deprotonate a proton that is not conjugated. Remember, alkane pKa is around, 50? That's not very acidic. But once you are going after a proton that's conjugated, or that gives you a conjugated negative charge, conjugate base left behind, now you're well within the realm of possibility and realistic chemistry because of the stability of the anion due to resonance. Also, making Grignards, we saw that in the previous chapter. Making Grignards is so much easier when you're working at an allylic position, again stabilized by the pi system next door, just like the SN2 reaction was in making these systems. And then again, the carbon next door is negative, and that's stabilized by the pi system further. So these become much easier, more manageable when you're making Grignards that are conjugated. A little bit more about pi systems. So remember that another way, an alternative way to write both of the resonance contributors is to represent it in one diagram, whereby the pi electrons are, represented as the arc, because they're somewhere between here and here, and there's an overall negative charge. So we can reduce this. Orbitally, each and every one of those carbons is sp2 hybridized, right? Each conjugated carbon is sp2 hybridized, and it has a p orbital with an unhybridized p orbital. And we represent the p orbitals, those unhybridized p orbitals, as parallel to one another. The electrons are flowing, therefore, across, they're kind of being shared across these overlapping parallel p orbitals. We were doing that in the Diels-Alder reaction as well. We were using the unhybridized p orbitals to represent the pi electrons, the domain of the pi electrons. Now, the pi orbitals, or the pi bond orbitals, are in the same alignment as the orbitals on the right bearing the lone pairs. Thus, resonance can occur. So ultimately, conjugation means that the p orbitals have to be aligned. If the p orbitals are 90 degrees or orthogonal to one another, they are not conjugated. So in order to, be related to each other, to pass the electrons from one to the next, you have to have those p orbitals aligned. Here's an example, and we can use those unhybridized p orbitals to explain why one of these systems is more stable than the one on the right. So carbon 1, 2, 3, and 4. I'm going to do what I did with the Diels-Alder, and I'm going to just do it in a row. 1, 2, 3, 4. Carbons 1, 2, 3, and 4 are all sp2 hybridized, and they all have an unhybridized p orbital, which allows them to distribute. There's 4 pi electrons, 2 on the one double bond, 2 on the other, but these 4 pi electrons are distributed across. They can be hot potatoed across all of those overlapping parallel p orbitals. So these 4 carbon atoms are said to be conjugated. They have a relationship with one another. Carbon 1, 2, 3, 4, 5. Well, 1 and 2 have unhybridized p orbitals. Then there's carbon 3, then there's carbon 4, and 5. Now, carbon 3 is not sp2 hybridized. Carbon 3 is sp3 hybridized, tetrahedral. It does not have an unhybridized p orbital. In fact, it has, tetrahedrally, it has 4 sp3 orbitals. So therefore, it doesn't have an unhybridized p orbital that's allowed to be in the same plane as the p orbitals on 1 and 2 and 4 and 5. So it's sort of like a wall. It's a blocker. It does not allow the 2 p orbitals, or sorry, p electrons on the left and the 2 pi electrons on the right, 4 and 5, to be conjugated. There's a blocker. They can't talk. They can't share across. So therefore, there is no conjugation. Those are isolated double bonds with no resonance. In practice number 2, we can try and represent 1, 2, and 3 and see if there's any resonance here. This is called an allene. And we've seen these before. You guys were using them from time to time or having them in your homework, but an allene is actually not considered to be conjugated. Let's use our p orbitals to figure out why. If we say carbon 1 and carbon 2, carbon 1 and carbon 2. So here are the pi electrons shared between 1 and 2. So would you agree that carbon 2, as I've drawn it, carbon 2 is a p orbital sharing with carbon 1 2 electrons. So it's already got 2 electrons in it, right? When you share, you count them for yourself. Carbon 2 also has p orbital overlap with carbon 3 sharing electrons, but I can't draw another orbital over the same. I can't use the same space, right? It's already used up. I already am using the y p orbital, so I can't do that. So if I'm using the y p orbital and the x is the sigma bonds, which I haven't drawn, then the p orbital I have to use for carbon 2 must be in the z direction. I'm going to color it in so you can see the difference. So carbon 3 also has to have a p orbital in the z direction to overlap with carbon 2. And now those electrons can be shared. They're in a different plane. I can't have 2 orbitals on the same plane overlapping, right, with 4 electrons in it. 2 electrons max per orbital. So I had to use the py and the pz in order to make this allene. The relationship between the py and the pz orbitals, although they're both unhybridized p orbitals, is not parallel. They're orthogonal to one another. Therefore, the 2 electrons in the 1,2 double bond are not conjugated to the pi electrons in the 2,3 double bond. Even though on first glance, if you just look at the allene drawn out, you'd think, oh yeah, they're conjugated, but they're not. They can't be. Carbon 2 can't do both at the same time. Now here's something interesting, kind of like Zaitsev's rule. Over time, people went into the lab and studied the stabilities using delta H chemistry, right? So you can figure out through this exothermic reaction using hydrogenation, right? So we're going to hydrogenate the double bond. You're going to do it in a controlled vessel such that if it's exothermic, you can evaluate the heat given off by the reaction. So therefore, it's an exothermic reaction, gives off heat, and you can measure that, okay, in kilocalories per mole. So if I took this butene molecule and I hydrogenated it in a controlled vessel, I determine that experimentally we get negative 30.3 kilocalories per mole. Okay, so that tells me the exothermic reaction of one double bond to do hydrogenation is negative 30.3. So then you go and you say, all right, put your scientist hat on and say, if I had 2 double bonds on a molecule, and I put it in a calorimeter and I do a hydrogenation and I calculate, I would actually guess double negative 30.3, right? Double, because I have 2 double bonds, so hydrogenating 2 double bonds is going to be double negative 30.3. So it should be about negative 60.6. And look at, this is experimental. That is exactly what they see, right? So 2 double bonds on a molecule, hydrogenation, you're going to get double the heat released, negative 60.5 measured kilocalories per mole. Beautiful. All right, so then I put in this 1,3-butadiene, and I would estimate negative 60.6 again, and instead, that is not what I see. Instead, I see negative 57.1, and you might think, oh, well, that's close enough. It really isn't. That's negative 57.1. That's like 3 to 4 almost kilocalorie per mole difference. That is amazingly large, massive difference, okay? And the question was why? So scientists were like, oh yeah, it's going according to plan, and then they throw in this system. So what does this double bond system have that the others do not. Well, if you said conjugation, you'd be correct. So what they noticed was that they were not getting as much energy released. Why? It's more stable. It's lower in energy, so it has less potential energy to give off when hydrogenated. So if you're lower in energy, you're going to give off less heat. So that's an interesting fact we're going to come back to. So long and short of it is, conjugated systems are more stable. They help us when we're running reactions. And as you saw in the Diels-Alder reaction, we can use these conjugated pi systems to do chemistry. This slide formally shows you that you can rotate around the sigma bond despite there being resonance and conjugation and sharing of electrons across that sigma bond. There can be rotation, and the rotation favors the S-trans configuration. And this is why we fight it a little bit when we do the Diels-Alder reaction, because we need the S-cis, but it's less favored when we do a Diels-Alder reaction. So unless it's in a ring, these Diels-Alder reactions can be a little sluggish because we're waiting for the equilibrium rotation to be S-cis. But why is it so difficult? Why is it difficult for the S-cis to form? Well, yes, it is steric hindrance, but you know what? You're also, I'm going to do it in my pi system again. Right? Because remember, these all have p orbitals. So when they're all set, when they're all aligned, you're sharing, right? But what happens when you have rotation? When you have rotation, you're having to pull two of the p orbitals out of alignment in order to get to the other rotated system. So by rotating, you're breaking this conjugation. You get it back when you make the full 180 degrees, right? Because you're rotating 180 degrees to go from cis to trans. But in that 90-degree state on its way to 180 turn, it ends up breaking conjugation. You've got Y here, but they had to go in the Z as they start rotating to get to S-cis. So for that brief moment, you've got to break conjugation. You can imagine that conjugation being stabilizing energy force. This is not an easy thing to do. This is why it's tough to go back and forth between S-cis and S-trans, and S-trans is favored due to steric hindrance issues. Okay, I want to go back now to the kinetic versus thermodynamic control that I hinted at in a previous slide. Let's reevaluate a reaction that we saw in the alkene chapter. We could take an alkene and react it with a strong acid. The mechanism, pi base. And you guys have gotten really good at telling me, 1, 2, 3, and 4. 1, 2, 3, and 4. The hydrogen's going to go on 1 because you guys have been very good at telling me that the carbocation would much rather be at the more substituted position. But I'd like you to add a little bit more now to this scenario. Yes, carbon 2 is more substituted. And it's allylic, it's conjugated. So not only is it more substituted, but you're also having a far more stabilized carbocation due to conjugation. So that is definitely going to be the preferred product, or I should say intermediate. And then to finish off the reaction, you guys got comfortable with doing the SN1. But like SN1, we were always at the stop, look around. Is there something better, right? In this case, we're not going for secondary to tertiary. However, I'd like you to add the stop and look around and add resonance to that. Because indeed, there is resonance. I could form the cis or the trans double bond with the primary carbocation, all in resonance with one another. Each one of these gets me to a different product. So I have 1, 2, 3 different products to consider. Wow. This is where kinetic versus thermodynamic control can be considered. So I'm going to come back to that one. If we had started with this system, just like we did. So this is our starting material. Okay, our starting material. And we added the HBr, just like what we did. I immediately form, with pi base, the secondary carbocation. Now, kinetic control, I want to remind you that when I say kinetic, I want you to think easy, low energy, meaning picture yourself on the couch, okay? You're on the couch and I always think about it when I was a kid because we didn't have a remote control for the television. We had one of those televisions that had a power button that you pulled the button to turn the TV on and you pushed the button in to turn the TV off. And whenever I was falling asleep on the couch and I wanted to turn the TV off, I had 2 choices. I could get up off the couch and go push the button in and then sit back down. But oh man, I was so comfortable, right? That would require me getting up and walking to the television, shutting it off, and then lying back down. That's the right thing to do, right? But it's going to cost me some energy. The easy low energy thing to do would be to maybe, I don't know, find something nearby and then throw it at the television and hope that it hits the button and shuts the TV off. That would be the easy low energy thing for me to do. So that's how I always imagine kinetic. Kinetic means fast, easy. Does it always get you what you want? Sometimes, right? But not always, right? Maybe you missed the button. It didn't get you what you want. Thermodynamic is the better thing to do. This one is going to perhaps take higher energy, but it's going to lead you to a more stable product. So thermodynamics is all about the product. Did I get the best outcome? Is the product the most stable? So it's very product focused. Kinetics is not about the product. It's about the process, right? The transition state. So what governs kinetics is the transition state. What governs thermodynamics is the outcome, the product. Okay? So if I started with this material here, and I was operating under kinetic conditions, meaning low energy, low temperature, so we can show this low energy by using low temperatures. And I'm going to do it in the shortest amount of time. It's very quick, right? Very, very snappy. So kinetic control means I use low temperatures, I run the reaction very quickly, and I get what I get. That's going to lead me to the HBr reacting with one of the pi bonds, You form the secondary carbocation, and very quickly, boom, kinetic control, you're going to put the Br. Everything's very fast. Okay? Now, is the product over here on the left the best we can do? Well, you can see right here, I say it's the less stable product. So this is not the thermodynamic product. This is the kinetic product. This is what I generate when I just do things very fast at low temperature. If I were to give it some time, if I were to heat the reaction and give it some time, I can favor the resonance that's occurring to give me my thermodynamic product, thermodynamic control, placing the bromine on the end. Why? Because the double bond is more substituted. But this isn't where the double bond was, right? So there had to be some resonance stabilization, and then find the more stable situation. This might take more energy, but it'll lead to a more stable product. So this would be thermodynamic control. What I want you to do is to practice this kinetic and thermodynamic control. Consider all the possibilities for HBr reacting with this diene. And then think to yourself, if I did this reaction fast, what would I get? If I did this reaction slow with higher energy, what would be the best double bond possible? This whole chapter on conjugation has been one massive lead up because, at the end of the day, it really is review. It's putting resonance into context with all of the chemistry that we did. If you think back to it, we studied resonance very early on. We were doing acid-base reactions, and the R of ario. You guys have been working with resonance and allylic positions for quite some time now, okay? But then we started to do some chemistry, alkene reactions, SN1, SN2, and what this chapter allowed us to do was to go back to the chemistry and understand how resonance can play a role in these reactions. What we're going to do next is we're going to be looking at very special conjugated pi systems called aromatic rings. Benzene is just one example of an aromatic ring, but we're gonna use benzene for the most part for all of our chemistry. Now, what you'll notice about benzene is that it is very conjugated, right? Look at the double bonds. If we were to write p orbitals instead of the double bonds, you'd see that every single carbon of the benzene ring is sp2 hybridized. They're all right next to each other, so all of the electrons are conjugated around and around that ring. And that's why we can draw a shorthand model of benzene with a circle. It doesn't matter, because of resonance, it does not matter how you draw the double bonds in a benzene ring, because they're actually not set due to this resonance. So it really doesn't matter. If you've ever wondered, oh, how do I know where the double bonds are? You don't. It doesn't matter, because they're just fully conjugated around and around with one another. Now, benzene is unusually stable. It is a very, very stable system. And although you could say, oh, I have double bonds, I could do hydrogenation, I could do HBr, I could do Br2, I could do ozonolysis. The answer to any one of your alkene flashcards with a benzene ring is no reaction. It is so stable that none of the typical reactions, osmium tetroxide, hydroboration, oxymercuration, none of those work on the benzene ring. So if I put a benzene ring with any one of those traditional alkene flashcards, the answer is just no reaction. So one of the nice things about benzene, though, is that it is highly conjugated. And so if you think back to lab, what reagents were you using when you were running TLC? Remember, TLC, you were spotting your compound on silica, and then you were using UV light to visualize. Why is that important? Well, UV light is only going to be reactive with conjugated systems. So conjugation is a requirement for UV light detection. So if you put a sample into a UV instrument to get a wavelength, you are only going to get it if the molecule that you're studying is conjugated. Just like we're only going to see a spot on the TLC plate if the molecule is conjugated. Since these benzene systems, and look, there's another double bond off of it with another double bond carbonyl. These are highly conjugated systems. Therefore, we see them, we visualize them using UV light. UV active. And that's important. Otherwise, if you've shown your UV light on the silica and the molecule was not UV active, were not conjugated, then you would see nothing. So go back and take a look at all the molecules you've been working with in the lab that you've been running TLCs on, and you'll notice that there is a conjugation relationship with the pi systems. Now, this relationship to UV light, as mentioned in the UV NMR IR chapter, is important, right? Take sunscreens, for example. Certain sunscreens, like the organic sunscreens, in most, probably 90+% of the sunscreens on the market, if you go to the store and you look at read the back of every sunscreen bottle, it'll have one or a mixture of the compounds shown on the right. So the way that organic sunscreens work is that they absorb the UV light because they have these conjugated pi systems, and they release the absorbed energy in the form of heat. That's how they work. They take the hit, they absorb the UV light instead of your skin, right? And then they dissipate it as heat. Now you want to be careful because we're trying to avoid exposure of our skin to UVA and UVB rays. Okay, these are the ones that cause damage and ultimately could lead to things like skin cancer. There are also inorganic sunscreens. These are ones that don't contain carbon, like titanium dioxide and zinc oxide. These are the ones I like. They're far more effective against UVB rays, but the best one known, the SPF, you can read a little bit more about this article, but the SPF, the sun protection factor ratings, they pertain to UVB rays for the most part. So there's really no good way of looking at how well one sunscreen does for UVB versus UVA. Avobenzone, shown in the middle here, is the one that offers the best protection against UVA radiation, which can penetrate deeper. UVB tends to do the most damage, but UVA you need to have protection against both. So, a mixture of these is great. I like the titanium dioxide and the zinc oxide, although they don't work into your skin very well because they're not organic, they're metallic. They work not by absorbing UV, but by reflecting the UV rays. They're like a metal, right? So they're reflecting the UV rays off of you. So finding that perfect mixture, maybe with a little bit of avobenzone in there so that it works into your skin and you don't look like a pale ghost, because the metals don't work in your skin as much, you know what I mean? Like they make you white, while the organic ones, they tend to work in and they don't look so horrifying when you're wearing it.